Hi, we're here from Microsoft to talk to you about innovations that we've been working on in the Linux and WSL space. My name is Jesse Natalie. I'm a developer on Direct3D at Microsoft.
And I'm Steve Pronovo. I'm the lead for the Windows graphic kernel, also at Microsoft. And we're super excited to talk to you guys about some work we've been doing over the last year on Linux, and especially on the Windows Subsystem for Linux. And we have 3 talks this year that we prepared together for XDC. So this talk specifically is about how we're bringing GPU hardware acceleration inside of WSL. So I'll be talking about how it works on like the kernel side of things and the host side of things. And Jesse's going to be talking about the user space. And then we have a second talk where we're going to be talking about like how we're bringing also GUI application to WSL. So the ability for user to run X11 and WLAN application.
And then after that, I will have a talk about work that we've been doing inside the Mesa project for building mapping layers for OpenGL and OpenCL on top of D3D, both for use on Windows and WSL.
We hope you enjoy our talk. So what is WSL? WSL stands for the Windows Subsystem for Linux. And in short, it's an infrastructure in Windows that allows a user to run Linux application. And in particular, Linux console application. So you can think about it at the high level. Windows is hosting a version of Linux, and the user can go and launch application within that environment, and then those application gets integrated back onto your Windows desktop. But today, this is only a console experience. It means you can run whatever you want as long as it's a console application. And why WSL? Like, why can't a user already do this by, for example, just creating a virtual machine in Hyper-V and loading Linux inside the virtual machine and running Linux application that way? You can totally do that. But managing the VM is a little bit of a pain, and it's not very user-friendly. With WSL, we're trying to enhance the developer experience to make it easy for a developer that needs to go and use tools that run in a Linux environment or tools that run in a Windows environment to be able to use both of those from the comfort of their PC. So, you know, they may have some tools that work better on Windows. They may have some tool that works better on Linux. And this gives them a way to basically run their entire workflow in the entire environment. And essentially get the best of both worlds without having to deal with like clunky setup of like, you know, dual booting into Windows and then Linux, or having to deal with multiple PC, or having to manually manage a virtual machine. So WSL today looks something like this, where like the screenshot I have like a Windows command prompt, and I also have basically like a bash on Ubuntu, where basically that this is an actual version of Ubuntu. You can log into it, you can go in and launch application, and standard out is essentially like forwarded back to Windows, so it looks like just a regular console onto your PC. So you have this nice terminal integration, but it goes beyond that. So we do things like, for example, file system integration. So your like Windows files are automatically mounted inside of the Linux environment. So it's very easy to go and access your files. And similarly, all of your files in the Linux world are available on the Windows side through like Explorer. We also enable things like Linux and Windows interrupt. So if you have a tool that works better on Linux and you have a tool that works better on Windows, you can have a Windows tool go and call an executable inside of Linux and wait for some result from it. And similarly, a Linux tool can basically go and call into like a Windows tool. So you can have script that basically bridge the two worlds. And there's many more. But the key thing today is that it's a console-only experience. So today we have 2 forms of WSL that you'll hear us refer to, WSL1 and WSL2. WSL1 essentially is we were running just the Linux user space, essentially inside like what we call the Pico process. And you can think about we had a special kernel trap, so that as the process calls it to kernel, we would go and trap these, and then we would emulate a Linux kernel on top of like NTOS. And this allowed us to run like Linux application, but as you can imagine, it had some performance issue, it had some compatibility issue because we could not perfectly emulate like a Linux kernel. With WSL2, we further improved this to now start running inside of a virtual machine instead of running inside of a Pico process. And one of the things that this basically allows us to do is to now run like the full Linux. So we run both user space, but we also now run an actual Linux kernel. So that gives us better performance. It gives us better compatibility. But it's fundamentally the same experience. So you can go and run your console application, and the standard out of those applications gets rerouted over and integrated into Windows. But it's overall much better than WSL 1. So when we talk about WSL, so that's been a feature that's been very popular with our developer. Like nowadays we have lots of developer that needs to go and do development on like many different platforms, and they have lots of tools that can only run sometime in Linux or maybe run better in Linux than the Windows version. And some of the features that like developers have been asking us to is one, having access to the GPU from within WSL. So mostly for compute, like a developer that wants to do like AI or machine learning. And in particular, the request has been hey, can we get access to NVIDIA CUDA to run their workload? But in general, things like TensorFlow, PyTorch, or any other framework. And how we go about adding the GPU inside of WSL, that's essentially going to be the subject of this talk. The second feature that's been requested from WSL is to go and extend WSL beyond a console-only experience and be able to allow like GUI application to run. And that's going to be the subject of our next talk on how we're going to extend WSL to be able to run X11 and Wayland applications. Okay. So yeah, so this talk is all about how do we basically bring GPU hardware acceleration inside of WSL. But before we dig into like the approach that we took and how we're implementing this, it's good to kind of take a quick step back and see how do we actually want to achieve that, right? So at the higher order bit is we want to go and share the GPU with the host. Like we don't want to go and dedicate a GPU to the host. Like, you know, there might be a single GPU on the system and the host still need to be able to use that GPU. And we want to make all of the GPU that the host has available to the Linux side of things. And we want to enable essentially both process in Linux and process in Windows to simultaneously be able to submit work to the same GPU and let our GPU scheduler and our GPU memory manager allow both of them to go and use the GPU. So we want to enable also like flexible management of resources. And what this basically means is we don't want, for example, to do fixed partition of the GPU. So we have other GPU virtualization technology that we use, for example, in our Azure cloud that allows us to take the GPU and essentially like split it into like pieces and then hand off pieces to like various virtual machines. And then each of these virtual machines basically have exclusive access to that piece of the GPU. Well, on a client scenario like this, that's not really good. Like, you know, imagine if our user is a student that may be doing some homework and some research project and needs to run under Linux, and then decide to take a pause and go play a video game. We want to make sure that, like, hey, as you launch the game, even if you didn't go and kill the virtual machine, the fact that the virtual machine is not really doing anything, it's mostly idle, we want VDMM to have the ability to go and take all that memory, send it out, give it all to the game so they can have a gaming experience. And as he's done gaming and wants to go back, at that point, we can reassign all the resources to whatever work he's doing inside of Linux. So essentially treat processes that are running inside of a virtual machine the same way that we treat a process that's running locally. And we want to enable this across a broad set of API. So we want to enable CUDA, we want to enable OpenCL, we want to enable OpenGL, and potentially like more API into the future. You'll see we'll talk about DX as well. So we're bringing DX12, but the way to think about us bringing DX12 is really as an implementation detail that basically allows us to go and achieve this goal of running OpenCL and running OpenGL by essentially creating layers on top of our DX12 driver. So that's a way essentially of bringing those API across a large number of vendor and a large number of driver without having everybody doing a large amount of work. So how do we actually achieve this, like sharing the GPU with the virtual machine? So we achieve this using a technology that we call WDDM GPU virtualization, or GPU PV for short. And to understand a little bit more about WDDM power virtualization, I'll take a little step back and talk a little bit about WDDM and then go into how power virtualization works and how we're extending it for Linux. So WDDM stands for the Windows Display Driver Model. It's a really thin abstraction of the GPU, and you can think about it as like the lowest layer on Windows where all the various API are built on. So the role essentially of WDDM is to abstract the GPU in an API agnostic way and allow various API to do things like allocate memory and creating devices and submitting work to the GPU and things like this. You can think about it in terms of, on the Linux side, the closest equivalent would be like DRM and KMS. And power virtualization essentially refers to the fact that the hardware that we use isn't actually built for virtualization. We achieve virtualization through software enhancement. And the level of abstraction in our power virtualization is essentially the WDDM interface. We take that interface and that abstraction to the GPU where all of our user mode drivers are built on, and we essentially project that into a virtual machine. And this allows the virtual machine to have access to like those services, and then you can go and implement the same API. So we don't actually project the whole of WDDM. We project a subset of WDDM that is enough for what we call compute or like, rendering engine and things like this. So we don't project, for example, display related things and other stuff of the sort. And WDDM power virtualization was designed for exactly these kind of like scenario. And it's used today for hosting Windows guests in various scenarios. So for example, we use this for Windows Defender Application Guard, where we run the browser inside of a virtual machine for increased security. It's used in things like the Windows Sandbox. It's used in things like the device simulator. So if you're doing HoloLens development and you don't actually have an HoloLens, you can basically run our emulator, and our emulator provides GPU acceleration inside of the virtual machine that's running the emulator. And then the idea here is to extend that support for Linux guests. So in addition to running Windows guests, we'll now be able to run Linux guests. So what does the WDDM architecture look like at a high level? So at the very heart of WDDM is the graphic kernel. This is where like our memory manager, our scheduler for the GPU reside. And it's essentially the component in the Windows that is responsible for sharing the GPU and managing the GPU across all the various processes that wants to go and use it. And the graphic kernel works really closely with another component that we call the KMD, or the kernel mode driver, that's provided by our ISV partner. And the KMD, you can think about it as like the HAL, or the abstraction that we're using to actually touch the hardware. So the graphic kernel never interact with the hardware directly. We always do it through a DDI, through the kernel mode driver, and the kernel mode driver is the one that ultimately go and touch the hardware directly. And then the graphic kernel exposed to user mode what we call the WDDM services, or the D3D KMT API. And these are the API that, like the low-level abstraction API, that all of the high-level API or higher-level API are based on. So when you take something like a Vulkan or OpenGL, OpenCL, CUDA, or things like this on Windows, the API typically has a user mode driver that, in the case of OpenGL, CL, and things, this we typically call ICD, or installable client driver. And that driver provided by the partner essentially goes and calls directly into these D2D KMT API to go and talk to their GPU. For D3D, it works something kind of very similar, where we basically run the D3D API, and we also have a user mode driver that, in this case, we actually call UMD, or user mode driver. You see often we actually interchange the name ICD and UMD, and we call them all UMD. But like the main difference with the D3D model is that rather than having the user mode driver call directly into like our kernel services, they basically just go and talk directly with the D3D runtime, and the D3D runtime manages talking to the kernel on their behalf. And the WDM services are really kind of low-level abstraction of the GPU that tries to be like API agnostic. So they do things like enumerating all of the GPU, being able to create a device on the GPU, be able to create context or hardware queues, be able to allocate memory, be able to go and map GPU virtual address to some of these buffer, to create synchronization object, to submit work. And all of this is in an API agnostic way. So for example, from WDDM perspective, when it allocates memory, it doesn't really care if it is for a Z buffer for the 3D or whether it's for like a shader in CUDA. And then the goal of the WDDM essentially is to isolate process or like entity that are trying to use the GPU from one another, right? And as the process try to talk to the GPU, each process is isolated into their own GPU virtual address space. They can go and allocate their own memory. If process wants to explicitly communicate to one another, we have mechanism to create shared memory and shared sync object and things like this. But by default, the process is kind of in its own little bubble. And WDM essentially offer that ability to go and create like different environment that the GPU can run on, and all of these are like fully isolated from one another. And then WDM, for example, will decide like, okay, which of these is resident at the time, or which of their memory is resident, etc. So WDM is already designed to essentially allow multiple clients to go and use the GPU and get the GPU schedule like fairly among them. The idea of the approach that we took to share the GPU with a virtual machine was to take this WDDM layer and essentially say, hey, we need to project that inside a virtual machine and makes the same service available. So that from the point of view of the kernel, a process, whether it's running locally on the machine or whether it's a process that is running inside of a virtual machine, it all basically look the same for the GPU scheduler and the GPU memory manager. So how does that work? So you can take it on the host inside of the Windows kernel mode. We're running this WDM GPU virtualization, and it exposes an interface over the VM bus. It exposes a protocol that allows guests to go and have access to the GPU. This part is completely agnostic of the type of guest. So the guest could be various versions of Windows, it could be Linux. This is all identical. Like the host does not actually has to worry about whether it's talking to a Windows guest or a Linux guest or which version. Like this is a fully version interface. In the case of Linux, we essentially go and wrote a kernel driver inside of Linux that goes and talk over that VM bus to go and expose the GPU to Linux user space. And we expose the GPU through this new dev.dxg device. So we have to expose it through this because we could not expose it just as a, for example, DRM device. Like DRM, the model kind of expect kind of a real GPU that they control and things like that. Versus in our case, what we were trying to go and do is to go and say, hey, we want to bring these WDDM services that allows software that was written against that GPU abstraction to be able to run inside of a Linux environment. So we have dev.dxg, and then dev.dxg through some magic in libdxcore, we make the same WDDM services, the 3D KMT API I was talking about earlier, available essentially inside of Linux. And this allows us to take like drivers, for example, like CUDA, and essentially recompile them for Linux to be able to go and access the GPU through that interface. So you can think about, like, for example, a driver like CUDA. The driver, like the major portion of the driver is already cross-platform, right? It's the same code that runs on Windows, that runs on Linux. And then the driver has a little like HAL layer that goes and deal with like the differences between the platform. And you can think about that HAL as being divided into two portions. So there's a portion of the HAL where the libcuda has to deal with the differences between, say, allocating memory on Windows versus allocating memory inside of Linux. And there's another portion that deals with how do you talk to the GPU itself. And in this case, essentially, what we worked with NVIDIA on is to go and say, hey, can you recompile your CUDA driver using your HAL to talk to Linux? But when you go for the OS, but when you talk to the GPU, go and use the WDDM interface. And so that gives us kind of an hybrid driver that gives us, for application, the CUDA surface, but that allows us to run it in that environment. And then we did something similar with D3D12, where we ported our D3D12 on top of WDDM, and then we've asked our IHV partner to go and compile their driver. And this allows us to go and get more API by leveraging things like Mesa, and be able to go and create CL on 12, GL on 12 layers that gives us access to these API on top of this D3D12. This DXG kernel, like Linux Edition, is open source. Like, we have the code on our fork of the Linux kernel. And the two things that you should keep in mind for this kernel is that it's not a straight pass-through. We say like, hey, we're projecting the API. Yes, like fundamentally there's, the memory manager and the scheduler are fundamentally on the host. So there's auto requests we have to go send on the host to basically go and do. But you can think about some API are implemented locally, some API are implemented remotely, some are implemented in a combination of both. The other thing is we also try to not do any data copy. So all the data that goes over the VM bus is essentially control information. Like, we try really hard to make sure that as, for example, the user mode driver goes and write a command buffer, the command buffer that's being written by the driver is exactly the command buffer, that the same memory that the GPU is going to read from. We don't make external copy. So I'll just go quickly over to kind of show a little bit how we go about doing that, where, like, how do we give, for example, CPU access to like our GPU memory. So when we allocate GPU memory, some of that memory is going to require CPU access. So things like, for example, a command buffer that the driver writes into commands for the GPU, or index buffer, vertex buffer, constant buffer, or all kind of buffers like that. So the way to think about it is, on the host, we have this process called VMM, and this is essentially where we host the memory of the virtual machine. So if you have a virtual machine, for example, that has, 8 GB of memory, we just allocate like 8 GB of virtual address inside of that process. And then through the magic of SLAT, we basically project that, and that becomes the RAM of the virtual machine. That's what we call a VA back VM. So even though the VM thinks it basically has a bunch of like RAM, like, that's kind of non-pageable, it's basically the RAM. On the host, that memory is virtualized. So like, we can page it out and do other stuff if it's not actually in use. As we load the Linux kernel, that's the RAM that it's running against. So when we initialize the DXG kernel inside of the Linux kernel, it basically goes and take a range of addresses in the CPU physical address space that we're going to use to manage access to our video memory surfaces. So in user mode, or in user space, when you have an application that goes and asks for memory to be allocated, that request goes over to the DXG kernel on the Linux side. And then that request gets sent over the VM bus, and VMM inside of the host goes and create that memory inside of the VMM process. And then through the same SLAT magic from before, that memory essentially gets projected inside of the WSL VM. So that once we go back to the Linux side of things, the DXG kernel inside of Linux can basically map a user pointer to that memory. So once that's set up, what user space in Linux has, it has access to the same underlying pages that the GPU is basically going to read. There's no copy of data or trap or anything like this over the channel. So if that surface, for example, is a command buffer, these are the commands that the GPU is going to go and read directly. So that example is for system memory. But if, for example, you have VRAM, and like, for example, that VRAM is visible over the PCI bar, we basically have mechanism that allows us to kind of take that virtual address and map it back and forth between like a IO address over PCIe or like a system memory address. And we can even do that while it's actually being actively used. So even if you have, for example, a thread inside of Linux that is actively writing to a surface, and VMM decides, hey, I need to demote this surface from VRAM to system memory, we can, through this mechanism, essentially put like, the SLAT in error, so that or the PTE invalid, so that has the thread access it will pagefold. The pagefold handler will recognize that, like, oh, okay, that address is being modified. Then we can go copy the data from video memory back to system memory. And then once the transfer is finished, we can refix up the PTE and then retry the access. And then the thread on the other hand will have kind of stop in the fault handler, but otherwise would not have noticed that basically the memory moved from one location to another. So this support is coming with WDDM 3.0. So all of our driver going forward will have built-in support for Linux. This is going to be validated as part of our certification process. So all of our partners are essentially adding systems that are configured for Linux into their test pool. And we have tests that goes and validate that like, yep, the driver works correctly inside of Linux. And the idea here is to really create an environment that out of the box, things already work. And now I'm going to hand it off to Jesse to go over the user space portion.
Thanks, Steve. I'm here to talk about basically what we have in WSL for user space graphics. So I just want to quickly reiterate some of the goals that Steve had talked about. Our goal is to support the breadth of existing Linux compute APIs, for example, NVIDIA CUDA, OpenCL. We eventually would like to have graphics APIs like OpenGL and Vulkan as well. We would like to make sure that we minimize any unnecessary or redundant work that our driver vendor partners would have to do. We want to support hardware-accelerated machine learning frameworks, for example, TensorFlow. And it's very important to understand that we are not trying to introduce any new competing APIs at this point. We're really just trying to support what already exists in Linux, your existing apps. When we approach the problem of how to get compute acceleration in WSL, we kind of saw two possible approaches. So the first one was to basically ask all of our driver vendors to port all of their ICDs for every API that we care about. It's a lot of work. The second option was to ask the driver vendors to port one graphics UMD, and then we could layer everything else on top of it. Specifically, if we ported D3D, then we could build layers to support all the rest of the APIs in terms of D3D. The ICD approach meant that we would have to continue to ask vendors to port new ICDs for every new vendor, for every new API that we cared about. So that could be at least 3 APIs across at least 4 vendors, where the mapping layer approach really means that we need one UMD from every vendor, and then one mapping layer per API. It's a much better scaling solution. It also enables us to leverage the DirectML backend that we have for ML frameworks, for example, TensorFlow. And it also helps contribute to Windows as well. We can continue to use these mapping layers to decrease the vendor burden of supporting Windows. It is still possible, of course, for ICDs to be ported. For example, NVIDIA's CUDA does work this way, as Steve mentioned. They basically just talk directly to the D3D KMT APIs. But in general, the approach that we think is more scalable for long-term graphics in WSL is to build mapping layers on top of D3D. So what have we done today? The lowest level piece that Steve already talked about, DXCore, provides some APIs for enumerating GPUs and querying properties. You can kind of think of it as roughly equivalent to what the DRM render nodes provide through their user API. We also have D3D12, libD3D12. It does require a D312 UMD to be present on the system. And at this point, we do have UMDs available or in development from all of our Windows GPU vendors. Actually, just a couple days ago, NVIDIA announced that they have a D312 UMD for insiders as well. And basically, this is the same D3D that we have on Windows. Layered on top of that, we have DirectML, which is a machine learning framework, a layer on top of D312 that helps provide highly optimized GPU-accelerated ML operators. And on top of that, we have TensorFlow, which is a widely used ML framework. We have a DirectML backend for TensorFlow available today. So some comments on the things that we've already built. Like Steve mentioned, all of the stuff that we're talking about, even though we call it graphics, we are mainly just focusing on compute acceleration. And when I say compute, I'm not trying to say that you can't do rasterization or you can't do, for example, ray tracing. What I really mean is that there's no window integration. So you can do rasterization, but you're not going to be able to see the contents unless you pipe it out to a file or do some other way of visualizing it. Just to reiterate, the intention of D3D in WSL is really as an implementation detail for GPU acceleration. It is really just to host other mapping layers for existing APIs on top of it. We are not trying to introduce a new API for apps to target directly. We don't have any plans to ship an SDK for D3D and WSL. It's really just an implementation detail. Yeah, it's really only there to allow higher level frameworks and APIs to use it. The D3D stack is the exact same code that runs on Windows. All components involved were modified, like Steve mentioned, just to dual compile. So it's basically the exact same thing. We fixed a lot of non-conformant code while we were doing this. As I'm sure some of you already know, the MSVC compiler is not necessarily conformant, and we had a lot of code that relied on that. So this was actually a great exercise for fixing a lot of that debt. As part of this process, we went ahead and replaced a bunch of Windows-specific constructs, like critical sections, for example, with cross-platform code, heavily relying on STL and C++ runtimes. We basically wrote a header shim that kind of replaces Windows.h so that we don't have to rely on the Windows SDK. And it provides roughly compatible defines and type defs to what our codebase and API expects. So for example, the D3D API has all caps uint, for example. We provide a type def for that maps to something that works roughly the same on Linux. And we're cross-compiling with Clang. And this process actually caught several real bugs because Clang's warnings are significantly better than MSVC's. So this was, again, a great experience for improving the quality of our code. A few notes about TensorFlow. It is TensorFlow on DirectML. One of the primary reasons that we went ahead with a DirectML version of TensorFlow for WSL is that it runs on a wide variety of hardware. If you wanted to use CUDA for compute, that would only run on NVIDIA. If you wanted to use, for example, ROCm, that would be a limited set of new AMD hardware. But with DirectML, we support all of our vendors. And not only do we support them, we kind of provide a guarantee of consistency and conformance because we test and work with all of our hardware vendors to make sure that we provide consistent results across all of our vendors. It's easy to set up. You just do pip install, and then you have TensorFlow with DirectML. And it is now open source. We've been working very closely with the TensorFlow community to bring this code upstream as well. At this point, we currently only have a fork of it, but we would like it to be available in the official builds of TensorFlow going forward. So something that's a little bit kind of interesting and unique about what we're doing here, most code on Linux ships as source, and it's expected that each distro kind of compiles their own source. We are shipping binaries. So we are doing our best to be distro agnostic with how we do this, across both Microsoft Code, D3D and DirectML, and the drivers that our IHVs are providing. Basically what we're providing is not quite statically linked binaries, but as close as we can get. So really the only external dependencies that we have are on the C library. Everything else is statically linked, so the C++ runtime, and any other dependencies that we have. We are making sure that we don't have any exceptions crossing module boundaries, for example, so it shouldn't really matter, what we're linked against versus who's calling us is linked against versus what the drivers are linked against. We are technically linking against muscle in our build, but we're doing it in a glibc compatible way, and as far as we have been able to test so far, it does appear to be giving us binaries that really do work in a wide variety of distros. At this point, our primary target is glibc-based distros, but we would like to make sure that we support everybody to the best of our ability. So what is next? Some things that don't exist yet. We've already mentioned that we would like to bring OpenCL on 12 and OpenGL on 12 mapping layers, both of which are heavily leveraging Mesa for their compiler and runtime infrastructure. At this point, we have both of these working on Windows, but we haven't yet started any efforts towards getting these working in WSL. And OpenGL specifically, if we wanted to get window integration, that is a very hard problem to solve. There's a lot of open design questions about how we do that. Not intrinsically due to the way that Mesa or GL is structured, but just it's a hard problem to solve because our devdxg graphics acceleration is not quite the same as what is already expected by Mesa, but I think that is a problem that we can solve. And there is already some work underway in getting GUI integration for WSL in general. So the next talk that we will be doing is Steve talking about our plan for getting non-accelerated Windows system integration with WSL. That is the X11 and Wayland applications in WSL talk. And I do have a quick demo. So as you can see, this is basically a WSL terminal that is running TensorFlow. You can see that Task Manager is running next to it, showing that it is running on an Intel device, and it is heavily leveraging the GPU, which is something that it wouldn't be able to do before this integration. And then some more info on how to try it out. You can check out aka.ms/GPU in WSL docs for more information. And that's it. And now we can open up for questions.
Okay, we should be live.
Yep.
So we have wait a second.
Is there a problem?
No, it's just I'm hearing myself. Okay, so I just took out the headset. So we have multiple questions. The first one from Robert Foss. Is there an entirely open source software userspace tag? I guess it's made from the WSL DX, the kernel driver.
At this point, no, we don't have a full open source stack. I guess there's still some echo going on. I don't hear any echo on my side, though. Yeah, at this point, we don't have any open source user space, unfortunately, but that is something that we are looking at. We're trying to work with our vendors to get an open source user space with on top of DebDXG.
Very good. Next question is
Steve, I think you're trying to talk and you're muted.
Yeah, sorry. Yeah, I was just saying we have like partially open right now because like all the Mesa part up to DX is open. But then after that, DX is closed. But yeah, like Jesse was saying, we're looking at to see if we could get some API to be like fully open, to have at least one example.
Sorry, could you just keep on reading the questions? I'm gonna try to fix this echo.
Yeah, sounds good. Let me take a look again. Next question was, is WDDM GPU scheduling also closed source? And yeah, at this point, the GPU scheduler portion is hosted on Windows. So that is currently part of the Windows kernel and is closed source. Next question, the slides on an overall architecture will be available after the talk. And yes, we're planning to upload the slides to the X.Org website after the talk. Next, this is not for gaming. Just to clarify, at this point, we're looking at compute, machine learning mainly. Next question from Robert Foss. Could DXG kernel conceivably be built as part of the Linux DRM subsystem? That way other Linux drivers could take advantage of APIs like DirectML. We are interested in upstreaming the DXG kernel that we've built so far. Right now, the DXG kernel that we've built only acts as a per virtualization driver on top of a Windows host. It is not a self-contained GPU scheduler, though potentially building something like that is possible.
Yeah, the key thing with DevDXG is really about trying to share the GPU with the host. So that's why we build kind of like this separate infrastructure to be able to do that. Like we did not see a way where we would be able to build this as a actual like DRM driver. We could have used a DRM driver if we had done something like discrete device assignment, where we take the GPU and just assign it to the VM, right? But then the host doesn't get to use it anymore. Or if we had like what we call GPU partitioning, where we can slice the GPU like in virtual function and assign a virtual function. But again, resource management wise, that's not very nice. Plus today, like the hardware is only on server class hardware that have this support.
Next question, what is our long-term goal for this project and how much of it can be upstreamed? Steve, do you want to start?
Yeah, so basically the long-term goal is to really make WSL an interesting part for developer, right? So that like folks that need to go and use Linux and need to go and use Windows to not have to deal with 2PC or reboot or anything like this. So to be able to do as much Linux stuff inside of Windows and be able to kind of bridge the gap between the two. WSL has been around for a little while. We see this as really, really critical. Like, although it's for kind of a small number of people, like, my mom will never go and run that. It's for developer, and we see developer as like really important, like the whole like Steve Ballmer, like developer. So it's about making like this environment better and better. So the GPU is really critical. And then we're bringing GUI app, and then we want to put it all together.
And how much of it can be upstreamed?
Yeah, so we're hoping that like all the pieces can be upstream, so it can basically be like completely open. There are things like DX, like there's some of us that would love to make it like open source. That's a more difficult discussion, maybe one day. But like all the pieces, like you'll see later, like all the Weston and things like this, like changes that we're doing, like it's all going to be open source. Our vGPU projection, anything that's on the Linux side of things, except for like the little DX piece, is going to be open source.
Next question is, can we know whether we have plans to support AMD ROCm compute stack for WSL2?
Yes, I don't want to talk on behalf of AMD. That's more of a question for AMD. But you can imagine, given CUDA is there, there's probably interest from like other competing compute API to kind of do the same.
Yep. Next question, can the per virtualization that we created be used independently of WSL with just any VM?
Short answer is yes. Like, any VM, like any VM hosted by Windows, because it's fundamentally built on like on Hyper-V and VM bus and things like this. But yes, you can use this in a like Hyper-V VM, for example. You can use this on an HCS VM. The main thing is if you go and use it in an Hyper-V VM, then there are certain things that you kind of have to go do like manually. Like we don't kind of package it all up like automatically for you. Like, so for example, if you install like a version of Linux inside of an Hyper-V VM, you won't automatically get the libdx core, libd3d. They're going to be like on the host. You can go get them from the host, and then you can copy them inside, and then that will give you like the bridge necessary to go and run like our various layers. Versus in WSL, we kind of do a bunch of magic where these files from the host are automatically mounted and map into the right place. So like as we create the VM and instantiate user space, everything is already set up and working. Versus if you do your own VM, then you kind of have to piece things back together. But if there's interest on this, we can share like the recipe, because most of our development was actually done that way originally.
Yeah, and the other thing that I'm going to add to that is one of the primary reasons that we're interested in upstreaming our DXG kernel Linux driver, is so that you can just take an off-the-shelf Linux distro, and it has this per virtualization driver built in, and then all you need to do is set up the user space correctly. Next question, do we intend to also support ARM 32 and 64-bit? Yes, at this point we do have plans for ARM64.
Yeah, ARM64 only.
And that's all the questions that we have so far. And I guess we're actually just about out of time as well.
Well, we still have like 32 seconds. So is the echo fixed now? Everything is fine.
For me now.
I mean, I don't hear myself twice. That helps a lot. And then apparently the cathedral is also gone, which I guess is a bit sad, but we'll deal with that later.